Hello. Hey guys. Hi guys. You saw the email I sent out. Just like last time, today's class is gonna be over 40 minutes. Most likely it's gonna be over 40 minutes.
How's your progress in learning how to solve?
So if you need to leave early at 40 minutes, then you can do that. And then you can watch the YouTube recording later on.
I'm asking for your progress.
Say again.
I'm asking for your progress.
And also today is the last pre-algebra class. And yeah,
That's
it's the
what
last
I'm
one.
asking.
There's no more after this. At least there's no more pre-algebra. I might be teaching some other classes later on. But this is the last pre-algebra class.
So how's your progress?
How's my progress?
Yeah.
Like my progress?
Yeah.
Like what kind of progress? What could I
The
improve?
Rubik's Cube.
I think I've gone better at teaching classes, maybe.
No, I mean like the Rubik's Cube. How's your progress?
I think you guys have
Solving it.
made a lot of progress as well. All of you have been working really hard throughout all these weeks, and I'm really proud of every single one of you. All right, 8 o'clock for me at least. So share my screen with the PowerPoint. All right. So as you can see on the screen, week 12, and what we're doing is counting and probability. All right. And the PowerPoint is very colorful today. All right, one more minute, and then I'll get started.
You still didn't tell me your progress on solving it.
Oh, my progress on solving Rubik's Cubes? Oh, well, I haven't really made much progress, unfortunately.
What do you mean? Did you even try Google searching it?
No. All right.
No, trust me, it's actually gonna be easy.
All right, then. Okay. So there's one thing I've learned from this class is I need to learn how to solve Rubik's Cubes. Okay. So it's 8:01.
Wait, what?
I'm gonna get started now. Today we're gonna go over counting and probability. Okay, so topics are what is counting? And then we're gonna talk about counting with addition and subtraction, counting with Venn diagrams, counting with multiplication, counting with casework, and then probability. Okay. And counting and probability are like very intertwined, and they're almost exactly the same thing. Okay. So what is counting. Well, first of all, do you guys know how to count? Let's count together. Let's count to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wow, we already know counting. It's so easy. So yeah, that's all I'm going to teach today. No, just kidding. So counting is actually not as easy as you think it is. Counting is counting. So counting is when you're trying to find how much of something there is. The definition of counting hasn't changed, but sometimes we're going to deal with counting in different ways other than just counting to 10. So a common example you might have is, let's say, how many ways are there to roll a dice? If I flip a coin 4 times, how many different ways, how many different combinations of heads and tails are going to come up? So that's like the counting we're going to do in math. It's not going to be like actual counting numbers, but it's going to be like more real world applications. Okay, so I think you guys already know how to count already. So here's a common example. Let me draw out some circles here. If I asked you, can you count how many circles there are on the screen?
12.
Well, you would say 12. That would be easy. But did you actually count every single one of these circles? No. You know that there are 3 columns, 4 columns and 3 rows. And so 3 times 4 equals 12. You have 12 circles. So in counting, a lot of the time, you don't have to count every single item. You don't have to count every single one really slowly, like 1, 2, 3, 4, 5. There are a lot of tricks you can use. As you can see here, you knew that this was an array of 4 by 3. And if you multiply them, you'll get the amount of circles there are. All right. So this means that in counting, there's not really a certain formula I'm going to teach you to use when you see a problem, because there's not really a formula dedicated to this specific kind of problem, right? For this thing, because you just know it. Okay. So for counting, I'm not going to be going over formulas, but I'm going to be going over some really key strategies that you're going to use when you solve counting problems. Okay, so let me go over the first one of these strategies, counting with addition and subtraction. So addition and subtraction are one way we can count things. All right, so it's better if I give you an example problem and then you can see how I would use addition and subtraction to count. Okay, so let me give you an example. If I had a list of numbers 4, 5, 6, all the way to 26, okay, I have this list of numbers, okay? What if I asked you, can you count how many numbers are in this list? Well, the first way you would do it is, I would just write all of these numbers out. But that's going to take a very long time.
The answer is 23.
Just like with the circles, you could count it like this, but it's not efficient, right? It's going to take a very long time. It's not very smart, okay? So how do we find this? Well, for counting, we always want to look for patterns. So first of all, let's label these numbers. That's the least we can do. Let's say 4 is the first number, 5 is the second number, 6 is the third number, okay? So let me call these our counting numbers. And let me call 4, 5, 6, and 26, all those are target numbers. So let's look for patterns between our target numbers and our counting numbers. Well, the first thing I can see is that for every single pair of counting numbers and target numbers, you subtract 3 from the target number to get to your counting number. 4 minus 3 is 1, 5 minus 3 is 2, 6 minus 3 is 3. Okay? Well, this pattern is going to stay the same for the whole list of numbers. So 26 minus 3 will get me to 23 as the final number in our counting numbers list. All right, so now what? Well, I've kind of like simplified the problem, right? Because if you want to count the numbers from 1 to 23, that's obvious. There are 23 numbers from 1 to 23, right? That's a lot easier to calculate than 4 to 26, right? You don't really know what that is, okay? So you try to simplify the list so that you can turn it into a list that's more countable. That's a list that's more easy to count. Okay?
Whoa, whoa,
So you
whoa.
want to look for patterns when you're counting. Okay? So that's really all there is to it. All right? Let's do these problems now.
What was that?
Once you get your answer, please chat that to me, and I'll let you know if you're right or not.
Wait, these are problems from the pre-algebra book that I have.
Are they?
They are.
No, I thought of these myself.
Wow, that's cool.
Like, they could be similar, but I don't think they're exactly the same.
Yeah, that's what I think. No, they are the same.
Exactly the same?
I still remember them. They don't have the exact
Wow, the luck.
same wording, but they have some of them have the same.
But it's not exactly the same question.
Okay, I got the answer for the second one.
All right, one more minute. All right, so I'm going to explain these now. So for the first problem, we have a list of numbers, and we want to make it easier to count. Right? We don't know the numbers from 9 to 89, but we can count the numbers from 1 to some other number, right? So that's going to make it easier. So let's write out a counting numbers list, 1, 2, 3, 4. So the pattern is that we subtract 8 from every target number to get to our counting number. So that's the same for the last one too. 89 minus 8, 81. So 81 numbers in this list. Okay, so we've made this list simplified so we can count it more easily. Okay, I'm going to do the same thing for the next one, but you got to be very careful here. Okay, because this question is tricky because they're not jumping by 1 anymore. Every term in this list is increased by 2. So what do we do now? How do we make this into a counting list like this? Well, since they're all even numbers, well, why don't we just divide them all by 2? Then we're going to have 4, 5, 6, 7, 44. Oh, Now we can just subtract 3 from each of them. So we have a counting list. 1, 2, 3, 4. Oh, 44 minus 3, 41. So 41 items in that list. Okay? For the last one, how many multiples of 4 are there between 25 and 101? Well, this problem is just like the other two, except it's worded a little differently. So let's just write out the multiples for, like some of the multiples of 4. So it's going to start from 28, 32, 36, and it's going all the way to 100. Okay, so that's the list. Now it's just like the others. We can divide through by 4. So we're going to have 7, 8, 9 to 25. So we divided by 4. Now we can subtract 6 from each of them to get to 1, 2, 3, 19. So 19 numbers in this list. Okay? So it's basically all the same thing. You try to make this list as simple as possible by using multiple manipulation strategies. Okay? So, one more problem for addition and subtraction. Once you get your answer, please chat that to me. So if you're a little stuck, I would recommend drawing out the circle to visualize how the circle works. All right, one more minute. All right, so quite a lot of people got this right. So let me go over the answer. So in kindergarten class, we sit in a circle for reading time. We all have an assigned number, and the first person is the number 1. I am number 7. The person on the opposite side of the circle is number 18. How many people are in the circle? Well, let me draw out a circle. Why not? So I'm right here, number 7. And on the opposite side, we have 18. Okay, and then number 1 is going to be like somewhere over here. Okay, so the numbers increase this way. Well, now what? Well, how do we find out how many people are in the whole circle? Well, one thing we can notice is that since I'm from the opposite side of number 18, the amount of people between us on this side over here is the exact same amount on this side, right? Because since we're on the opposite side of the circle, the amount of people here is the same as the number of people here. So how many people are here? Well, it goes from number 8 to number 17. So we're going to find how many numbers are from 8 to 17. Well, subtract 7. 1, 2, 3, 10. 10 people right here, which means 10 people here as well. And then we have to add in 7 and 18, right? So we have 2 extra people. So 10 plus 10 plus 2, 22 people in total. All right. So as you can see here, there's not really a definite like formula you would use for a counting problem. You just have to break it down and analyze it so that you know how to do it. Okay. And then you would implement other strategies you might know beforehand. Like here, I use this strategy. Okay. Are there any questions? All right. Now we're going to move on to counting with Venn diagrams. So is there anyone that doesn't know what a Venn diagram is yet? I think most of you should know what a Venn diagram is.
Probably no one.
Okay, so Venn diagrams are actually a really, really great way to count things. Okay, Venn diagrams, you use Venn diagrams when the problem gives you some categories, and then it puts items into those categories. So look at this example problem here. We have 2 categories, Spanish and French, and it's putting numbers into those categories. So what we can use to organize this information we have is by using a Venn diagram, okay? A Venn diagram makes it a lot simpler to look at, and it makes it a lot easier to do, right? Because this information is too much for you to process all at once. Okay, so let's draw a Venn diagram. Well, we have 2 categories here, Spanish and French. Let me draw a Venn diagram. Spanish, French. Okay, so now we need to break down the information we have. 18 kids take Spanish. So what this means is that in total, 18 kids take Spanish. So that means the kids in this area right here. Those are the kids that take Spanish. Well, I can't really write numbers in right now because I can't really label 18 as this whole circle. Okay, so let's first look at the other information we have. We have 8 kids take both Spanish and French. This means that they belong in the intersection. So we put 8 in the intersection there. Okay. Then we have 5 kids don't take any language. Well, that means they're outside of the Venn diagram. They don't belong in either of those categories. All right. So now let's go back to 18 kids take Spanish. Well, if 8 kids take both Spanish and French, then that means only 10 kids take only Spanish, right? Because 10 plus 8 gets you to 18. All right, so now what? Well, we're given one final piece of information. There are 29 kids in the whole school. So this means that if we add up all these numbers here, only Spanish, both, only French, and neither, if we add all of those together, we'll have the number of kids we have in the school, right? Those add up to equal the total, right? Every single student must be in one of these categories. So if we add all these numbers up together, we'll have 29. So let's set x as only French. So that means 10 plus 8 plus x plus 5 equals 29. So what does x equal? X equals, wait, let me do some quick mental math here. 6, all right? So this is 6. Now we have our whole Venn diagram filled out. Now we can just look at what the question wants us to answer. How many kids take French? Well, this means we have to add only French with both French and Spanish because those both count. So 8 plus 6, 14. Okay, that's the answer. All right, so the Venn diagram was a great way to organize the information from this problem. Okay, and you could do this without a Venn diagram, but it would make it very, very hard. All right, so that's how you would use a Venn diagram for counting. Are there any questions? All right. Let's do these two problems here. 5 minutes. Once you get your answer, please chat that to me. I'm trying my best to answer, reply to yours. So if you didn't get a reply, you should be good. All right. All right. 2 more minutes. Alrighty, so I'm gonna answer, I'm gonna go to solutions now. All right. So at a sandwich shop, you can buy a sandwich, a salad, or both. 18 people went, 5 people only got salads, 3 people got both, and 2 people weren't hungry and didn't buy anything. How many people got only sandwiches? Well, let's draw out a Venn diagram. We're gonna have sandwich and salad. All right. So let's break down the information we have. 18 people in total. Well, that's not much use right now. So 5 people only got salad. So that means 5 goes here. 3 people got both sandwiches and salads. So we put 3 here. 2 people weren't hungry. They're outside of the Venn diagram. And remember that the rule is that if you add up only sandwich, both, only salad, and neither, we get the total number of people that are at the sandwich shop. So if we say only sandwich is X, then x plus 3 plus 5 plus 2 equals 18. So what does x equal? X equals 8. All right, so 8 people got only sandwiches. And that's our answer. Okay. Now there are two science classes.
You as an answer though.
There are two science classes, physics and biology. 20 kids take physics, 8 kids take biology. There are 3 kids that don't take any science class. So 24 kids in total. How many take both? So this is just another Venn diagram problem. We're going to have physics on one side and then biology on the other side. So 20 kids take physics. This means that 20 kids in total take physics, all right here, okay? So we can't really label that right now. So let's go on to the other information we have. We have 3 kids that don't take any science class. So 3 kids are out here. Now what can we do? Well, we want to find both physics and biology. So let's just say that is x. Well, then how many people take only physics? 20 minus x, because 20 is the total number of people that take physics. If we subtract x out of that, then we'll get the people that only take physics. And then similarly for biology, we have 8 minus x on this side. All right. So now we remember the rule that if we add up all these things together, we're going to have the total number of kids. 24 is the total, so 20 minus x plus 8 minus x plus 3 equal 24. If you solve for x, let me see, it's going to be 31 minus x equals 24, so x will equal to 7. Okay, so x equals 7. And 7 is the answer then, because x is the amount of people that take both, so 7. All right, any questions? Alrighty, we got one more Venn diagram problem here, but this time you need to make 3 circles. All right.
Monster hunting isn't a class though.
You know, it's been like 3 years since I read Harry Potter, so I tried my best, okay?
Okay, but then just put charms or transfiguration or astronomy or divination.
People are accusing me of bad memory in the chat. Sorry, guys. Now let's focus on the math rather than the Hogwarts part of it.
What is monster hunting?
All right, please stop.
That's not a hunt.
No,
That's not
stop.
the thing. It's like the same thing with defense against.
All right. Just pretend that it's a real class.
Seriously. And even if they were, they'd all be required.
All right, do the math, guys. This is probably going to take a while, so I'm going to give you guys 4 minutes for this one problem. Uh-oh, sorry. Yeah, so I think the numbers are a little big for this one. So if you made some kind of computational error, then I guess that's kind of really easy to make a computational error. So however, for this problem, if the numbers are like too big for you, then maybe you can use a calculator to confirm your answers. Okay, one more minute. A lot of you are really close to the right answer. All right. So I'm going to explain this one now. So this is just another Venn diagram problem, but you need to have 3 Venn diagrams now. So first we have defense against the dark arts, potions, and monster hunting. All right, that's a 3-way Venn diagram. So let's break down the information we have. 83 take defense against the dark arts, which means it's all in here. So that's not really much use for us right now. Let's go on to the other information we have. It seems like this is the easiest one to go for. 6 take all 3 classes. That's the first one we can really put in for certain. All right, now what do we have? Well, we have 10 take potions and monster hunting. So that means this is this area here. So this area is 10, which means this is 4, all right? Because it's 10 minus 6. 8 take defensive against the dark arts and monster hunting, which means this area is 8. So 8 minus 6, 2. Similarly for this one, 31 minus 6, 25. Right? So we're getting pretty close. Now we need to look at the other information we have. We have 22 take monster hunting in total. Now what does that mean here? Let me highlight this area. Monster hunting in total is right here. So all of this is 22. So to get what's in here, we do 22 minus 2 minus 6 minus 4. So what do you get here? We get, I think we get 10. Right? Then we have 101 take potions. Well, potions is right here. So to get this area, we do 101 minus 4 minus 6 minus 25. And if I'm not mistaken, that is 66. Okay, I might have done a math error there, but I don't know. So then 83 take defense against the dark arts. So 83 minus 25 minus 2 minus 6. So what do we have here? According to my paper, it is 50. Okay, so now if we add all these together, we'll get how many kids go to Hogwarts. So that's going to be 163. All right. So we add every single number in this list. So it's going to be 50 plus 25 plus all these things.
Oh.
Okay, so you might have missed some things in there, but the most important part was filling out this Venn diagram. Okay, so that's how you would do it. All right, let's move on. We have counting with multiplication. Multiplication is a very good way to count. Okay, so here's an example problem. At a restaurant, you get a main course, a side, and a dessert. There are 6 options for the main course, 3 options for the side, 4 options for the dessert. How many different meals can you have? Well, the answer for this problem is to multiply all 3 of these numbers.
72?
72, yes, correct. But why do we know how to multiply, right? Why would we multiply here? Why don't we add these things together? Well, we can make what we call a tree diagram. So let's say this is U. So 6 options for the main course. So this is kind of like a choose your own path thing. So you can go down 6 paths here for the main course. Right? These are 6 possible paths you can take for your journey through dinner. Okay. So now in each of these paths, you can take 3 options for a side. So each of these paths extend out to 3 sides. And each of these paths extend out to 4 options for dessert. And that's just too many paths, and I'm not gonna write that in. So basically, you did 6, and then each of these 6 had a group of 3 paths to it. So you did 6 times 3, and then each of these paths had a group of 4 to it, and then we multiplied finally by 4. Okay, so that's how we know we would use multiplication. All right, so whenever you do a counting with multiplication problem, you can always be able to draw a tree diagram with it. Okay, so let's do some problems here. Get your answer, please chat that to me, and I'll let you know if you're right or not. I think I'm gonna have a lot of answers for the first one, so I'm only gonna reply to you if you get it wrong. All right. When you give me your answer, please write what problem you're referring to. So 1, for the first one, you write 1 dot and then what your answer is. All right, so if you got it right, then I'm not going to reply to you because I have too much to reply to.
Okay, so the answer mine is correct.
All right, 2 more minutes. Ooh. So when you get your answer, please tell me which one you're referring to. Otherwise, I won't really know which one you're answering. All right, so let me go over the answers now. The first problem, I have 3 pants, three shirts and 4 pants. How many different outfits? Well, we do 3 times 4, 12. Why does this work? Well, we can draw out a tree diagram. First, we choose our 3 shirts. For each of these 3 shirts, we have 4 different choices for our pants. All right, 12, okay? Same for the second one. We do 4 times 2 times 1. We can draw the tree diagram. So first we choose our science classes. Wait, that's 5, never mind. We choose our science classes, then we choose our English classes, then we choose our math class. 8, okay? For the last one, there are 4 lights. Each light can be on or off. How many arrangements of lights can I have? Well, let's take this step by step. Let's just draw out 4 lights here. Let's first look at the first light. How many choices do we have for the first light? Like, could it be, how many choices do we have? Well, there are only 2, right? It could be on or it could be off. Let's make a tree diagram here. We choose our own path for the first light. We have 2 now. What about the second one? Also 2 choices. Well, our tree diagram has expanded once again. What about the third one? Also 2 choices. So we draw out 2 branches for each of these. Fourth one, also 2, so drawing out all those. And basically the gist is you do 2 times 2 times 2 times 2 equals 16. All right? Because basically every single light could be on, it could be off, right? There are only 2 choices for each light. So you do 2 for the first one, 2 for the second one, 2 for the third, 2 for the fourth. Multiplying them all together, you get to 16. All right? So this is the kind of step-by-step thing you want to do, okay? And this strategy is basically what you're going to do for the next problem as well. Okay, so keep in mind this strategy. It's going to be useful for the next problem. All right? So here are 2 more problems. I'll give you guys 3 minutes for these.
Wait, what do you mean by arrange them? Oh, I see, I see.
All right, 1 more minute. All right, so I'm going to go through these problems now. So I have 4 different books. I want to arrange them left to right on a shelf. So let's break this down step by step. Let me draw my bookshelf here. So how many choices do I have for the first book? Well, 4 choices, right? I can choose any one of my 4 books. All right, so that's kind of like doing a tree diagram. First book, 4 paths. What about my second book? Well, for my second book, I can only choose 3 now because I've already put one of them there. 3. Okay, so it's extended like this. Similarly, for the next book, I've already used 2 books, so I only have 2 left. And finally, we have 1 book. 4 times 3 times 2 times 1, 24. Okay? So this was really similar to the last problem. We have to take the first one, second one, third one, fourth one, and we take it step by step like that. Now for the last one, a palindrome is a word that is the same when spelled backwards. For example, race car is a palindrome. All right? So how many 4-letter palindromes can you make with lowercase letters? So how do we do this one? Well, for any kind of palindrome question, you're going to see this a lot. Pretend that there is a mirror right down the middle. So for example, in this problem, there's a mirror right down the middle of this, this palindrome, okay? And these are my 4 letters here. So there's a mirror down the middle. What does the mirror do? The mirror reflects things, all right? So if I say this thing is X, I'm just labeling this as an X. Then that means on the other side, there has to also be an X right there. If we say Y is here, Y has to be on the opposite side of the mirror. So what does this mean? Well, if we choose the letters for the first two, then that means they have to be the same letters for the last two, right? So we're not going to be able to choose a letter for every single one of these. We can only choose letters for the first two, because the first two determine what's going to happen in the last two, right? It's like a mirror. It reflects it. So we only have two choices for our letters here. So how many choices do we have for X? Well, there are 26 letters in the English alphabet. Also for Y, we have 26 as well. So the answer is just 26 times 26, 676 palindromes. All right. So palindrome, this word you're going to see a lot in counting problems. So our next strategy is counting with casework. What is casework? Well, casework is the strategy where you break a problem down by taking it case by case. So let me show you with this example problem here. Aliens on the planet Oye Funk have a special alphabet with 4 letters. Their words are all less than 4 letters long. How many different words can they make? Well, how do we do this? Well, let's take it cases. Well, it says that words are less than 4 letters. So what I can do is I can take one case as having 1-letter word, or a 2-letter word, or a 3-letter word. So those are my cases. I have 3 cases. My first case is that I'm choosing a 1-letter word. Second case, 2 letters. Third case, 3 letters. All right. So this kind of breaks the problem down to make it easier to do. Like I'm doing this problem in chunks now. So now I find how many 1-letter words there are. So how many 1-letter words? Well, we can use all 4 of those letters. All right. So 4 choices. 2-letter words. Well, I don't think it's going to be that much, so we can write them out. Let's say we have letter 1, letter 2, letter 3, letter 4. So we have 1 and 2, 2 and 3, 3 and 4. What else do we have? Wait, actually, what we can do, this is just like the other problem, right? So we can actually double these. So we have 4 choices for our first word and 4 choices for our second letter in this 2-letter word. So we have 16 here. 3-letter word, well, 3 spaces now. We have 4 choices for the first letter, 4 choices for the second, 4 choices for the third. 4 times 4 times 4, 64. All right. So now we've broken it down to cases. We have 4 possible 1-letter words, 16 possible 2-letter words, 64 possible 3-letter words. And now all I need to do is add these cases together, right? Because naturally we have to add all these together. And the answer should be 84. Okay. So casework, basically, it's just a method where you break a problem down to make it simpler for you to do. So you're kind of doing it in chunks now. Okay, are there any questions?
No.
Alrighty, so 3 casework problems. Sometimes the casework is not that obvious. So how about this, guys? Skip the 3rd question because we're running a little low on time. So the first one is a little hard. I think the second one is easier to do. One more minute. Alrighty, we're running a little low on time, so I'm going to explain these now. So the first problem, we're going to try to take it case by case. So what are our cases? Well, we can look at A, right? Obviously, A can be 1, right? Because 1 squared is 1, and then we'll have a lot of stuff for B. Then what is the maximum value for A? Well, we know that 5 squared is 25, and 4 squared is 16. So we're only going to need to look at 4 cases for A, because A can only go from 1 to 4. So let's start with our first case, A equals 1. Well, if A equals 1, then A squared is 1. 1 plus B is less than 24. B is less than 23. So B is the numbers from 1 to 23. 1 to 22, actually. So there are 22 values for B, which means that there are 22 possible pairs for A equals 1. Let's look at A equals 2. If A equals 2, then A squared equals 4. 4 plus B is less than 24. B is less than 20. So B is from 1 to 19. So we have 19. All right. Now A equals 3. A equals 3, then A squared is 9. 9 plus B is less than 24. B is less than 15. So B is from 1 to 14. 14. A equals 4, our final case. 16 plus B is less than 24. B is less than 8. B is from 1 to 7. All right. Now all we need to do is add up our values in our cases. 22 plus 19, let me just write it like this. 2 plus 9, 11. 22. 62. All right. So there are 62 possible pairs. All right. So sometimes the cases are not that obvious, but if you kind of break it down, then you might be able to look and find out what it is. Okay. So now for the second one, how many 3-digit numbers exist so that the hundredths digit is 2 times the ones digit? So let's take this like our digits. Let's fill in these digits. So how many choices do we have for our first digit? Well, the hundredth digit can't be 0, right? Because otherwise it wouldn't be a 3-digit number. But the hundredth digit is also 2 times the ones digit, which means it has to be an even number. So the hundredth digit can be 2, 4, 6, or 8. 4 choices. What about the middle digit? Well, there's not really a limitation on that one, right? So the digits can be from 0 to 1 to 2, all the way to 9. So we have 10 digits. 10 possible ways we can fill in the middle digit. What about the last digit? Well, the last digit has to be 1/2 of the hundredth digit. So if we already decided what the hundredth digit is, then that automatically decides what the ones digit has to be. So we only have one choice for the ones digit. 4 times 10 times 1, 40. So we first, this is more like a multiplication problem rather than a casework problem. But the cases were kind of like taking each digit one by one as a case. And we solve for the amount of possible digits we could have in each of those cases. All right. So I'm going to skip. Okay, now we have probability. Probability is defined as the chance of something happening. When something says, what's the chance of this thing happening? Then you would use probability. For example, the chance of you flipping a coin and landing on heads, 1/2, right? Because there are 2 possible ways. It could be a head, it could be a tail. If you flip it, there's a 1/2 chance of it getting on the head side. All right, so that's the probability of getting a head when flipping a coin. All right, another example of probability is if you were to roll a standard 6-sided die, like this, it kind of looks like this, right? Standard 6-sided die. What's the chance of getting a 1? Well, there are 6 sides, right? So 1 out of 6. Okay, so that's basically what probability is. So how do we connect probability and counting? the formula for the probability of something happening is defined as the number of successful outcomes divided by the number of total outcomes. Right? That's the definition of probability. We want to take what we want over what the total is. For example, if we implement this formula for our die, the number of successful outcomes would be 1, because there's only one way we can roll a 1 on the die. The number of total outcomes is 6, because it could land on a 1, a 2, a 3, a 4, a 5, or a 6. All right, so this is the formula for any kind of probability. So how does this connect probability to counting? Well, we use counting to find the number of successful, then we use counting again to find the number of total. And then we just need to divide those two and we'll get our answer for probability. All right, so probability is more like a counting problem, but we need to do 2 counting problems in one. Okay, so that's basically what probability is. So we take the number of successful outcomes, we have to use counting to find whatever that is. We take the number of total outcomes, we use counting again, and we divide those, we'll get our probability. All right, any questions about this? Any questions? All right, so let's do these 3 problems here. I know we're running a little low on time, so let's quickly breeze through these. So for the first one, if you get the correct answer, I'm not going to reply because I think there's going to be too much. Two more minutes. All right, so I'm going to explain this one now. So what's the chance of rolling a 5 on a dice? Well, number of successful over number of total. Well, there's only one face that will give us a 5, and there's 6 faces in total. That's 1/6, okay? Now you roll 2 dice. What's the chance that both dice roll a number greater than 4? So how many successful outcomes do we have? Well, if they both roll greater than 4, then they can only have a 5 or a 6. So the first dice can only have 2 choices for its number. The second dice can also only have 2 choices for its number. So we use our multiplication strategy. We have 4 choices in total, 4 successful outcomes. Now again, I can write this out. 5, 5, 5, 6, 6, 5, 6, 6. So this refers to the first dice, second dice. Right, so we have 4 possible successful outcomes. How many total outcomes do we have? Well, each dice has 6 numbers they could land on in total, right? 1 to 6. So we use 6 times 6 as our total. So it's 4 over 36. Simplifying, we get 1/9. All right. Now the next one, you flip a coin 8 times. What's the chance that you get a heads every time? Well, let's use successful over total. What's the amount of successful we have? We only have 1, right? Because that's heads, 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 heads. That specific order of heads, it's only 1. There's only 1 successful outcome. How many total do we have? Well, let's look at each flip. And let's label those in a line like this. Okay? So each flip can be a heads or a tails. So this one has 2 choices, 2 all the way down the line. We just use a multiplication to find the total. That's 2 to the power of 8, 1 over 256. So that's the chance you get a heads every single time. Now, what's the chance that you get at least 1 tails? Well, this is kind of hard, right? Because we could have 1 tail, we could have 2 tails, we could have 3, 4, 5, 6, 7 all tails. How do we find all of those? Well, we could use casework, right? But then we would have 7 cases to consider. That's a little too much. So the trick here is that let's look at both of these questions here. Do you guys notice anything similar between these? Getting a heads every time means that you have no tails. And that's the only case where you have no tails. And that's the only case where you don't have at least 1 tails. So if we do the total probability, which is 1, and we subtract that from the amount that we get a heads every time, we'll get the amount that we get at least 1 tails. So this is going to be 255 over 256. All right, so let me explain this again. The chance that you get a heads every time, that's the same thing as saying the chance that you get no tails, right? And that's the only other possibility other than getting at least 1 tails, right? Because this is the only possibility you could have that doesn't satisfy this requirement here of getting at least 1 tails. So if you take the total probability, which is 1, subtract that from what you have here, then you'll get what you have here. Okay, does everyone understand how this works? And there's actually a special word to describe what you're doing here. It's called complementary counting, all right? But since this is a pre-algebra class, I'm not going to go that much into detail about it, but you're going to learn that later on, okay? So let me skip this slide. So let's do the quizzes. But before we do that, I want to say a few words here. Since this is the last class, this will be the last quizzes we're going to do. And I just want to say that it's been a great time. I hope you guys have learned a lot. I certainly have. I've learned a lot about teaching. I've learned a lot about organizing things. This has been really helpful to me, and I hope it has been helpful to you as well. All right, so I hope you guys enjoyed this class, and I'll be teaching more in the future. So if you want me to go over something specific, then you could email me, and I'll be able to create a class for that. All right, and overall in the pre-algebra course, pre-algebra is not just algebra, right? We did geometry, we did number theory, we did counting and probability. Pre-algebra is a combination of all of these things, okay? And each of these topics, we went briefly over them. We didn't really go that much into detail, all right? So if you want me to teach any of these topics in detail later on, then please email me, and I'll see if I can make a course for that, all right? So now let's get on to our last quizzes of this class. Okay, so let me stop sharing this. Let me share my screen for the quizzes. Here it is, play live. Let me look at the settings. Alrighty. Joinmyquiz.com, let me copy the link here. Where's the chat? Here is the direct link. This is the last class because there's nothing else I can really teach about pre-algebra. All right. And there will be homework for this week. And not only will there be a homework, I will attach a review packet, which will review everything we've gone over in this course. And there's going to be a key for that as well. Okay. So there's going to be counting and probability homework and also a review packet. Wait, why am I here? Why am I in this game? What? My name is right there. Who is that? I am not playing this game, so who is it? Well, all right, so one more minute,
Wait,
and then I'll start the game.
That's funny.
Share my computer sound.
It might be real.
Is anyone having trouble getting in?
I just have one question. Can we start?
Can I start? Well, if there's no one else that if there's anyone that's having trouble, then we'll need to wait. 10 more seconds. Someone is drawing on my screen.
How do I turn on music? How do I turn on music?
I think the music's gonna play when I start the game. All right, so we're gonna start it, okay? No calculator
Okay,
allowed.
then start.
Okay,
Bye.
and
Isn't
enjoy.
that obvious?
Here it goes. I'm gonna say this. Please take your time on these problems. I think I've given you guys plenty of time to work through these slowly. Correct answers so far. 0 incorrect. pretty good as well. And in 6th place. wondering, I am not doing quizzes. Right? That's someone else. It's not me. Has 7 correct answers. Austin moves into 3rd place. So if you finish and you want to leave now, go ahead. And thanks again for a great 12 weeks of class. It's been a lot of fun.
So Rubik's Cube.
Like with any game, you join later on, I think I'm gonna have to remove you. Alright, so seems like the standings are finalized. Let me post them in the chat now. So first place, game code 876484. Austin. 3. Ryan. 4. Amber. And 5. How do I write that? How do I write number 5? I think I have a Chinese keyboard right here. Ah, I wrote it in. Alright.
Wait, how do you do?
Okay, so that'll be it for today. Let me end the game here. Let's look at our top 3. Third, Pi, I guess. Second, Austin. First place, the game code. Okay. So that's going to be the end of our last class together. Once again, it's been a great experience for me. I hope it has been a great experience for you. And this week, we're going to have counting and probability homework, but also a review packet you can work on if you want. And I'm going to have the solutions for both of those. All right. So thanks, guys. Goodbye. Goodbye.
Thank you.
Yeah, no problem.
Thank you. Bye.
Bye. All right.